everyone, this is Mrs. J, and today we're going to talk about conditional probability. First, I have a quick warm-up for you guys, so pause the video and give it a try. All right, go ahead and check your work here. So for part A, these are two mutually exclusive events because you can't be both even and equal to 3 at the same time. So you find the individual probabilities and simply add them up and simplify. For part B, these two events are overlapping. So you do need to subtract away the probability of them both happening, or the intersection. And in this case, all of the multiples of 6 are also even, so you're essentially subtracting away that entire probability, and you end up with just 1/2, which is just the probability of being even. So today we're going to be focusing on what's called conditional probability. So conditional probability is finding the probability of an event given that another event has already occurred. So again, if you see something like this, P of A with a vertical line B, that means that the probability of event A happening given that B has already occurred. All right, so we're going to start by trying to find conditional probability given a two-way data table. So here we have some data about some patients who took a medicine or didn't take a medicine, and then whether or not they got a headache. So we'll call event A the event that a person did not get a headache, and event B the event that a participant took the medicine. So in this first question, they say to the nearest whole percent. So this time we're going to be describing probability as a percentage. So usually we write it as a fraction or a decimal, but we can also write it as a percent. What is the probability that a participant who took the medicine did not get a headache? So the way this is worded, the condition is that the participant took the medicine. So here we're actually finding the probability that a person did not get a headache given that they took the medicine. So this is the probability of event A given B. So the given condition is that the participant took the medicine, and we're finding the probability that they did not get a headache given this condition. So to find this, well, we can start with all of the participants that did not, that took the medicine. So let's start with the participants that took the medicine. And if you look at your table, that would be 65 people. And then, so that would be our total number of outcomes. That's our sample space size. And then we want to find what's the probability that those people that you did not get a headache, and that would be 54 people. So the probability is 54 out of 65, which is about 0.83. So it's 83% chance. Okay, now let's look at part B. So this is to the nearest whole percent. What is the probability that a participant who did not get a headache took the medicine? So in this case, the condition is that the person did not get a headache. The participant did not get a headache is the condition. And so given that condition, what's the probability that they took the medicine? So in this case, we're finding the probability of event B given A. So we have to start with the sample space of the given condition, which is the participants who did not get a headache. So this time we're going to start with 76. So our total number is 76. And then we want to know of those people, how many took the medicine, and that would be 54. So the probability is 54 over 76, which is approximately 0.71, so about 71%. So again, the way that these are worded really matters. So you have to figure out which part is the condition, and then which part is the probability given that condition. All right, so now I have one for you to try on your own. So please pause the video and give it a shot. All right, so go ahead and take a look here. So in the first one, it says the probability that a participant who did not take the medicine got a headache. So this is the probability of event A given B. Because event A is getting the headache given that they did not take the medicine. For the second one, the wording is flipped. So this one, the condition is that the participant had a headache. So what's the probability that of those people that they did not take the medicine? So this is the probability of event B given A. And then you can see I found the numbers from the two-way table, and then I converted it to decimals. Oh, and then percentages. All right, so now we're going to practice creating what's called a two-way relative frequency table. So we're essentially taking all of the values within our two-way data table and we're turning them into decimals by dividing each value by the total number. So in this case here, the total number of participants is 100, but you would really divide it by whatever the total is to find the percentage as a decimal of each of these things happening, so that would be called the relative frequency. So if you go in and you divide all of these values by the total, which in this case is 100, that will give you the relative frequency for each box. So we can do this, and when we do that, it essentially allows us to look at it and quickly be able to determine a percentage of something happening. In this case, it's not too, the numbers look almost the same because the total number of people is 100, so we're dividing by 100. However, typically the total would be something other than 100. So just remember you're dividing each value by the total number of data points in your table. So now we're going to try finding some probabilities using our relative frequency data. And you can see that since we divided each number by the total number of outcomes, that these are already the probabilities of each individual specific set of events. So here event A is the event that a participant did not get a headache. So no headache is event A. Event B is the event that a participant took the medicine. So if we're asked to find the probability of event A happening, we can just look down or look across our no headache, and then we see it's 0.76, which is a probability. So there, since we've already divided it by our total, this is already a probability as a decimal, which is one way to write a probability. Now for the probability of event B, and I find my B, which is the participant took the medicine, and I see of all the people that took the medicine, we have 0.65, so that's our probability that they took the medicine. And then last, we want the probability of the intersection of A and B. So here, that would just be in this box, right here. Do it in a black. And again, since we've already divided it by the total number, this is that probability. So the probability of events A and B is 0.54. So for part B, we're going to be finding the conditional probabilities. So here we'd have to do just a little more work, but we're finding the conditional probability of event A given B. So we have to start with the given or the condition, which is that the participant took the medicine. So of the people that took the medicine, again, that total outcome would be 0.65. So A given B, our denominator will be 0.65. And then our numerator will be event A, which is the event that a participant did not get a headache. So we'll do 0.54. And then if I divide those two numbers, we get 0.83. And here we'll just leave it as a decimal because they don't ask us to write it as a percentage. And then for that last part of part B, the probability of event B given A. So let's start with the given. So it's given that the participant did not get a headache. So we're working with 0.76. So it's within this realm. And then the people that the participants that did take the medicine, of the people that did not get a headache would be 0.54, so 54% of the people. So when you divide those two decimals, you get 0.71, which again we'll just keep as a decimal. But what you might notice is from the 2 examples ago, we did the same exact thing but from our original set of data. So it wasn't the relative frequency data, it was just our frequency table. So we got the same exact answers. We got 83% and 71%. But again, here we're just using the relative frequency to do the same thing. So you may have noticed kind of a pattern of what we did to find those conditional probabilities when we were using our two-way table of data. So when we found the probability of A given B, our denominator was always the probability of that given condition. And then our numerator was always the probability of the intersection of the two. So it was of those things that are happening, how many were also we're also fulfilling event A. So there's a formula for this, and that formula is the probability of the intersection of A and B divided by the probability of B. So this does matter which one is the condition, because you see the event that is the condition will end up in the denominator of your probability. So just make sure when you're reading a problem, you are careful to interpret, which part is the condition and which part are you finding the probability for. All right, let's give this one a try together. So it says for a standard deck of playing cards, find these two probabilities. So first, the probability that a red card randomly drawn from the deck is a jack. Okay, so here, if we call being a red card event A, and if we call being a jack event B, and we interpret this, it says a red card that is randomly drawn from the deck is a jack. So the condition is that it is a red card, and they're saying, assuming that it is a red card, what's the probability that it is also a jack? So this would actually be the probability of B given A. So remember, for this, we need to find the probability of the intersection, and then divide that by the probability of the condition, which is that it's a red card. So let's start by finding the probability of the intersection. So I'll find that by itself. So the probability of being both a red card and a jack is, well, there's only 2 possible cards for that. So that's the jack of hearts and the jack of diamonds. And there are 52 total cards. So the probability of the intersection of A and B is 2 over 52. And then the probability of event A, which is a red card, is 26 over 52. Half of the deck is red. So to find that probability of B given A, we do 2 over 52 divided by 26. Sorry, this was supposed to be a 52 down here, not a 56. 26 over 52, and then we multiply by the reciprocal, and actually these will just end up canceling out, and we end up with 2 over 26, which is 1/13. All right, now let's look at part B. So this one says find the probability that a jack randomly drawn from a deck is a red card. So now this time you could see that event B is the condition. It's the condition that it is a jack. Then what's the probability that given that condition, we also draw a red card? So in this case, we are finding the probability of A given B. So again, being a jack is the condition, and then finding a red card is the probability that we're finding given that it is already a jack. So we're going to do the probability of A and B, the intersection of A and B, divided by the probability of B. Well, we already know the intersection of A and B is 2 over 52 from part A, but we still need to find the probability of event B, which is being a jack. So there are 4 jacks in each deck, so that one would be 4 over 52. So we do 2 over 52 divided by 4 over 52. We multiply by the reciprocal and simplify, and we get 2 over 4, which is 1/2. So the probability that you draw a red card, given that it is already a jack, is 1/2. Now, we were using that formula for these. I think you can also kind of do these with logic, which ends up with the same result as the formula. If you're finding the probability of a red card being a jack, well, we know that there are 26 red cards to pick from, and there are 2 jacks. So you can almost jump straight to the 2 over 26. And same thing for this one. If you're wondering what's the probability that a jack that you draw is a red card, well, there's 4 jacks and there's 2 red cards, so it's 2 out of 4. So again, this is something where maybe if it were drawn out in a two-way table, it would be even easier to do, but here, this is how you can do it using that formula. But again, logically, it should make sense to you why these numbers are where they are. All right, so I have one for you to try on your own. So go ahead and pause video. There's a little typo in here. This should say is a king. So if you could change this to king, that would be great. So pause the video and give it a try. All right, go ahead and check your work here. So just to kind of show what I did, I labeled the events A and B. You could label them B and A. It doesn't really matter what you call each event. But for this one, for part A, being a face card is the condition, because it's a face card that's randomly drawn, is a king. So finding the king is event B, and the condition is being a face card. So there are 4 cards that are both face cards and kings, so that probability of the intersection is 4 over 52. And there are 12 cards that are face cards, so there's 3 per suit, jack, queen, king, so notice ace is not a face card. So it's 12 out of 52, so we do the intersection divided by probability of A, and we get 1/3. The second part, being a queen, is the condition, because it's a queen that is randomly drawn, is also a diamond. So it's a probability of B given A. So the probability of both happening, well, there's only one queen that is a diamond. It's the queen of diamonds, so it's a 1 out of 52 probability. And the probability of being a queen is 4 out of 52. So there is a probability of 1/4 that it is a diamond, given that it is already a queen. All right, so that is all for today's video. Thank you guys so much for watching.